All right, welcome everyone to part 3 of our discussion on molecular orbital theory. So in the previous parts, we've kind of introduced the idea of what is molecular orbital theory and applied it to diatomic molecules and talked about that some more. Okay. Now we're going to do some examples of that and then talk a little bit about heteronuclear diatomics to finish up our discussion. So first example here, we have a diatomic molecule formed from lithium and lithium plus is predicted to be stable form, because why? So why is it predicted to be stable, right? However I wrote this, right? Why is this stable? Okay. And the options here have to do with where electrons are occupying bonding or anti-bonding orbitals. So we need to draw the molecular orbital diagram for lithium dimer. So for lithium dimer, right, lithium, if we're just focusing on the 2s, right, right, so we're just focusing on the 2s orbitals, right, you're going to form just a sigma star orbital, right? And if it's lithium plus, right, there's going to be one electron in a 2s orbital and none in the other one. So I'm just going to have one electron here. Okay? So this is what's going on for the 2s cases. Now the answers here have to do with more electrons than just one. So we also need to consider the 1s orbitals, right, 1s, right, and in the case for the 1s's, right, we're double occupying, right, and we're occupying the sigma and sigma star orbitals for the 1s, right? So in total, I have 1, 2, 3 electrons in the sigma bonding orbitals and 1, 2 electrons in the anti-bonding orbitals, right? So 3 electrons in bonding, 3 electrons in bonding. So A, B, and C, all the number of electrons in the bonding orbitals are correct, but then the number of electrons in the anti-bonding orbitals is 2. So A here is the answer. I have 3 electrons in the bonding, 2 electrons in the anti-bonding orbitals. This would have a bond order equal to 1/2, okay? Right, and so that would be the bond order of lithium, even though it's not asked for, right? The bond order of lithium dimer cation, right? Right. So next example here, right? If I remove an electron from N2, the nitrogen bond lengthens. Whereas if I remove an electron from O2, the oxygen-oxygen bond shortens, right? And the reason for this difference is what? Okay. So again, we're going to answer this question by drawing out the molecular orbital diagrams. So I'm going to focus on the valence orbitals, right? And so we have the sigma star for the s orbitals. Then for nitrogen, it goes pi. Here, let's try to not give myself a lot of space here, drawing these out. So this is the molecular orbital diagram for nitrogen, for N2. Okay, for O2, it's going to look like this. Okay, so this is the molecular orbital diagram for O2. This is it for N2. Again, I kind of don't have a lot of space here, right? So if I put in electrons into this diagram, right, for nitrogen, right, each nitrogen has how many valence electrons? So there's 2s electrons plus 1, 2, 3, 4. No, sorry, there's the 2s and then 2p, right? There's lithium, barium. No, it's carbon, then nitrogen, then oxygen. So there's 5. I don't know why I can't think of that off the top of my head, right? There's 5 electrons for each nitrogen, I believe, right? Because there's 2 in the s's and then 3 in the p's. Yeah. Okay, that makes sense. So there's 5 electrons in the 2s, 2p orbitals, so a total of 10 electrons. So I have a total of 10 electrons here, right? 10 electrons, and so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so if I notice here, these are my electrons I'm occupying, right? Well, note this is sigma, sigma star, pi, sigma, pi star, sigma star. Okay. Right. For oxygen we have 12 electrons. Oxygen has 6, right, in this valence space. So there's a total of 12 electrons for O2. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Notice here I put them in separate orbitals with the same spin. That's from Hund's rule, and that is going to be a lower energy electron configuration than if I doubly occupy one of the orbitals. Okay. And again, we'll note here this is a sigma, sigma star, sigma pi, pi star, sigma star. Okay. Right. So if we notice, right, for nitrogen, if I remove an electron, right, because that's what's happening, right? So now I've drawn an orbital diagram, so now let's answer the question, right? I'm removing an electron from nitrogen, and I'm removing an electron from oxygen, okay? Right, so if I remove that electron from nitrogen, right, then what's happening is I'm removing an electron from a bonding orbital, right? This is in the sigma bonding orbital, so I'm removing an electron from a bonding orbital. That's going to weaken my bond, which will strengthen or lengthen the bond, right? A weaker bond is going to have a longer bond length because the atoms aren't held together as tightly, okay? While for oxygen, when I remove an electron, I'm removing it from an anti-bonding orbital, so that's going to actually strengthen my bond, right? And that's why the bond becomes shorter, right? So the main reason this is occurring, right, is the electrons coming from an anti-bonding orbital in oxygen and from a bonding orbital in nitrogen. So C here is the main reason why this is occurring. All right, for this question, right, according to molecular orbital theory, which molecule would be the least stable? So to answer this question, we got to draw out the MO diagrams. Conveniently, all of these guys, right, are having the same kind of ordering of the sigma pi orbitals in the p space. So we don't have to worry about that. We can just use the same MO diagram for everything. Okay. So I'm going to start with the 1 sigma and 1 sigma star orbitals. These are from the 1s orbitals, right? And then I'm going to do the same thing for the 2 sigma star. These come from the 2s orbitals. And then we have the pi, sigma, pi star, sigma star orbitals. Okay, so that's my MO diagram. I'm including the 1s orbitals because of the hydrogen here. Okay, so for hydrogen, right? So let's fill in some electrons here. I'm going to start with the lowest. So for hydrogen, I just have the 2 electrons. So for hydrogen, I have a bond order of 1 because I have just 2 electrons in the sigma bonding orbital. Right. Next is going to be lithium. Right. Lithium, I'm going to occupy all 6 electrons that are in lithium, right? So for lithium, H2 dimer, lithium dimer, I have a bond order of 1 as well, because I have 4 electrons in the bonding orbital and 2 electrons in an anti-bonding orbital. Okay. Next to beryllium, beryllium is going to put 2 more electrons, right? It's got 2 more electrons in lithium. So you see for beryllium, right, our beryllium dimer, our bond order is 0. So this guy's not going to actually form a dimer, right? And then finally, we have carbon, okay? So carbon, I'm then going to put in how many more electrons, right? Carbon has 2 more electrons than beryllium. So I'm going to put in 4 more electrons total. And so there you go. So that's carbon. So for C2, that has a bond order of 2, right? If you add up all the bonding electrons and subtract off all the anti-bonding electrons, you're going to have a total bond order of 2. Okay, so that means that carbon is going to have the strongest bond, and it's going to be kind of the most stable. And beryllium is going to have essentially no bond, and it's going to be the least stable, right? So the answer here for what should be the least stable is BE2. so to finish this all up, let's talk a little bit about heteronuclear diatomic molecules. Okay, so we've talked about homonuclear diatomics, right? For heteronuclear diatomics, the molecular orbital diagrams look the exact same. You just have to take into account whether or not you have elements like oxygen and fluorine. Okay, and so the only time you use a molecular orbital diagram that looks like that of oxygen and fluorine, so the difference between the MO diagrams for lithium to nitrogen, right, is that you have your let's delete this so it's not confusing, right? Right. So the difference is you have your pi, then sigma, right, orbitals, while for oxygen to fluorine, right, you have I shouldn't have drawn that so low. Let's try that again, right? You have your sigma, then pi orbitals down here. Sigma, then pi. Pi star, sigma star, that's the same order. It's always pi star, sigma star, but it's sigma, then pi for oxygen and fluorine, and pi, then sigma for lithium to nitrogen. Okay? And so for your diatomics, basically O2, F2, and OF are the only things that are going to look like, the only one's going to have sigma, then pi. Okay? So if I have an oxygen bonded with a nitrogen, it's going to have a molecular orbital diagram like that on the left, right? So something like ON is going to be from here, right? F, C is going to be there, right? It doesn't matter if I have oxygen or fluorine. If both elements are not from the oxygen fluorine group, then it's going to look at the MO diagram on the left, okay? And so that's how we deal with heteronuclear diatomics. Is same type of MO diagram as homonuclear diatomics. We just have to take care of which MO diagram we use. Okay, so the example we'll do here, and to finish up these slides, is looking at the bond order of CO. Right. Because we have a carbon atom, right, that means we're going to use the MO diagrams that look like something like for N2 or C2, right? The main reason is because, right, while oxygen, the effective nuclear charge for oxygen makes the orbital small enough that in O2 dimer, they've reduced the repulsion between the electrons in the p orbitals and lower the energy, okay? Right, when you have the oxygen with the carbon orbital is still too big that it has too much steric repulsion, and it's not going to push those sigma bonding orbitals in the p space lower than the pi bonding orbitals. Okay. And so, right, and so we'll then use the fact that oxygen has 6 electrons, right? Carbon has 4 electrons. In the valence space, that we have a total of 10 valence, right? 10 valence electrons, right? We'll ignore the 1s electrons because whatever, it doesn't really matter. It doesn't affect our answer whatsoever. So typically we just ignore the 1s electrons if we can. And so here is drawn out what that molecular orbital diagram looks like for carbon monoxide, right? For CO, carbon monoxide. All right, the molecular orbital diagram is given here, right? Where I've drawn, so this is for carbon, this is for oxygen, right? And then these are the molecular orbitals, right? So the oxygen atom, right? And this is the carbon atom, right? That's an M, right? And so, right, for oxygen, we have 1, 2, 3, let's see here, 4, 5, 6 electrons here. For carbon, we have 1, 2, 3, 4. Okay. And I drew the orbital lines for oxygen a little bit lower than carbon just because of the fact that it's more electronegative than carbon. But again, right, and it has a larger effective nuclear charge, right? I guess how we've been describing it. And so, but that's not too relevant, right? What we care about is this final diagram where now I'm going to put in 10 electrons total. So, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So I see here I have 10 electrons, right? If I look, right, my bond order, right, for this, I guess we've been just using B, right, to get the bond order. So the bond order for this is going to be 3, right? So I'm going to have total of 8 bonding electrons, 2 anti-bonding electrons, and so 8 minus 2 divided by 2 is equal to 3. So that's my bond order. So I would predict from this molecular orbital diagram that carbon monoxide has a triple bond. Okay. And here on this slide is basically just, you know, in a much nicer way representing, right, where these electrons are going and things like that. Okay. And so this kind of wraps up our discussions of molecular orbitals and molecular orbital diagrams. Okay. So after this, we're going to start talking about spectroscopy.